Crap. All right, well, I guess there's 2 recordings here. The connection to the cloud server got disconnected, so I guess I'll probably end up having 2 recordings. We'll see, I don't know. But anyways, right, so as you're saying, right, the total internal energy for this process is 0, right? And this equals delta U1 plus delta U2, which is Q1 plus W1 plus Q2 plus W2. Okay? So this is true always. So if we go back to the lecture slides, right, A is definitely not saying that, right? W1 does not have to equal negative W2. That's only true if Q1 plus Q2 is 0, right? Same with B, right? Both A and B are not true. Now, if A and B was written as delta U1 equals negative delta U2, that is true, right? As we showed, right, delta U1 plus delta U2 equals 0. So one has to equal the negative of the other for them to cancel, okay? So, right, so that's true for the internal energies, again, because they're state functions, right? But it's not true for work and heat because they are not state functions, right? C here would say that delta U1 equals delta U2, which is not true. They have opposite signs, okay? And then D here, right, W1 plus Q1 plus W2 plus Q2 has to equal 0. That is true. So D, okay, is always true in this process, right? But the rest of these are not always true, okay? And again, this doesn't mean that delta U1 plus delta U2 equals 0, or sorry, W1 plus W2 equals 0, and Q1 plus Q2 equals 0, right? Doesn't mean the total work and heat are equal to 0. Just means the sum of the work and heat transferred during this entire process has to equal 0, right? But it could be that by the end of this, some net work has been done by the system and some net amount of energy has been transferred to the system, right? Right, that some heat has been transferred to the system and the system did some work, right? So it did work, so it gave off energy, but then it got that energy back from the surroundings, right? So its total internal energy stays the same, right? Thus delta U is equal to 0, right? But W total and Q total, if you will, don't have to be 0. They have to be equal and opposite sign, but they don't have to be 0. So questions about this question? All right. And we'll be thinking a lot about this type of stuff, about what are your changes of states, what are the relationships between, if you do multiple steps, how are they related to each other, what things we can write out, what can we say, okay? And later we'll then start talking about what is W, what is Q, how do I calculate those things, and so on. Okay? All right. So similar thing here, okay? I have, right, this is kind of a wordy problem, okay, but I have a state that starts in A, right? Some system starts in state A. I then change my system, right, undergo some change in state to state B, and during that change, right, there's some amount of heat that's lost to the surroundings, right, 35 kilojoules, and then some amount of work that's done by the system, okay? Don't know the exact total amount, but I know it's done by the system, okay? I then take my system and give it 13 kilojoules of energy, of work by the surroundings, right? And then I also give it 10 kilojoules of heat that I transfer to the system from the surroundings to get to state C. Then finally, I take my system and take it back to state A by doing 28 kilojoules of work on the system, right? So the work's being done by the surroundings. And then some amount of heat is transferred during that process. And then after all this is done, I know that the total amount of work that was done is 21 kilojoules by the system. Okay, so I know the work. The W total is 21 kilojoules that's done by the system, okay? And the question is how much work is done in the first step, and then how much heat is transferred in the last step, and to where? To the systems or to the surroundings, okay? So again, on Zoom, what I'm going to do here is if you'd like to try to talk with other people over Zoom, join the breakout room. If you don't feel like doing that, you don't have to join the breakout room. And then in a little bit, I'll close the room and I'll come back and talk about this as a class. And those right in the class, you're welcome to discuss with other people about this and kind of work on it. Now, I don't know if when you join the breakout room, you still see my screen or not. Hopefully you do. I haven't really played around with the breakout rooms yet, so hopefully you do. But let me move this so everyone can see the total problem, right? So again, this is kind of a wordy problem, but All right. So I'm going to go to this screen here. Right. So I'm going to try to slowly work up here. I should have written things in larger letters, but right. So I'm try to write it more clearly. This is right W1, right? Right. We know the total internal energy change, right, for step one, just the sum of the heat and work, and right. We know the first law of thermodynamics applies to all three steps, right? We also know that the total amount of work done is just a sum of the work from each three steps. And the total internal energy change is the sum of the internal energy from the three steps, which we happen to know equals 0, because again, like the other problem, right, we finished where we started, okay? And then writing down, right, all the things that we have, right, we're told for the first step that we have 35 kilojoules of heat transferred, right? That heat is being transferred to the surroundings, so it's a negative 35 kilojoules, right? We don't know about the work yet, right? Q2, right? In the second step, both work is being done by the surroundings and heat is being transferred to the system. So both of those are positive, so it's just positive 10 kilojoules and positive. And then the third step, right, the system is doing the work, right? So the work is done by the system. So it's minus 28 kilojoules, right? And then I don't know what the heat is, okay? But I have two equations here that I can use to solve for my two unknowns, okay? Yep. Oh, is it? Yeah, well, so let me, okay, yeah, and maybe I think, which step? First, second, or third? Third step, finally, I'll go back to A, doing 20 kilojoules of work. Oh, on the system. You're right. Sorry, my apologies. Yeah, that says on the system, right? So it's done by the surroundings. Sorry, I misread that. Thank you. So it is plus 28 kilojoules. Okay. Right, and I forgot to write down the total work. Right, was so W total is going to be negative 21 kilojoules because, right, it's done by the system. Okay. All right, so let me go back here. Thank you for catching that. Sorry. All right. Yeah. So sorry, that is a positive 28 kilojoules. Okay, because the work is done right on the system, right, by the surroundings. Okay. All right. And then again, W total is minus 21 kilojoules. So using all this information, right, we have W total, right? So W total, right, again, is W1 plus W2 plus W3, right, which is minus 21. And then W1, we don't know. That's what we're trying to solve for here. W2 is plus 13, and W3 is plus 28. Okay. All right, thank you. Negative 62. What W1 is, right? Again, it was told that work is done by the system, right, in that first process, right? And so it should have a negative work, right? So that's W1, negative 62 kilojoules, okay? Subtract 13 and 28 on the other side to get that, okay? Then we can use this other equation here to find out what the heat transfer is, right? I have the total internal energy change is 0, and then that's, right, delta U1 is just the negative 35 minus 62, okay? And then delta U2 is plus 10 plus 13. And then delta U3 is plus Q3 that we're looking for, and then minus 21. Oh, sorry, I just wrote down the total work. Yeah, my apologies. Plus 28. Sorry about that. I saw W here, and I was like, oh, that's W3. Right, plus 28. Okay. Right. So what? That's 51. That's 3. and minus a total of 97. Right, yeah, right, equals 0. So goes down to Q3. Right. So, right, my amount of heat transferred that third step is 46 kilojoules, right? And that heat is transferred to the surroundings is the positive value. Okay.
So it would be to the system.
Or to the system, my God. Thank you. Oops. Right. Right, heat transferred to the system, so it's positive 46. Thank you. Yeah. Do that to myself sometimes, right? So I always double check when I'm thinking about these things, but yeah. So again, heat is transferred to the system, right? Because again, and how to also refresh yourself to think about what sign that is and where the energy is going is thinking about what delta U needs to be, right? If Q is positive, that means, right, let's just say there's no work, right? And if I'm just looking at Q, right, assuming work is equal to 0, right, then delta U would equal Q. Oh, right, can't see that, thank you. Right, delta U would equal Q if work is equal to 0, right? And so if Q is positive, that means delta U has to be positive, which means the internal energy has to increase. And for the internal energy to increase, right, energy had to come into the system to cause that increase in internal energy, right? So positive Q corresponding to positive delta U means that energy was transferred to the system. Okay? And so this kind of relationship between Q and W and delta U I often use for myself to kind of make sure I have in mind, right, where is the energy going to, right, based off of how I expect the internal energy is changing and such. Okay. So questions about this problem? Okay. Right, the main key steps in this problem, this, is writing out the proper signs for these values of Q and W, and then writing out these two equations, right? Identifying, right, the total work is just the sum of each individual work, and that the same thing goes for the internal energy, but also the fact that the internal energy total change is equal to 0 for this problem, right? Once we have those two kind of initial steps, right, then it's just a bunch of algebra here to solve for the two unknowns in these two equations. Okay. Right. Again, throughout the semester, that's right how hopefully we kind of think about stuff and whatnot, right, is first is just trying to write down all the relevant equations and all of the things that we know in these problems, okay, right, because that is kind of the key step, right, and then after that, it's just using some algebra and some simple math, right, to then try to solve for whatever things you don't know, okay, but like if this problem was given, say, on an exam, right, the majority of your points would come from the stuff up here, right? This is where I would say, okay, did they do the correct sign for Q and W and things like that, right? Did they write out this equation? Did they write out this? Did they identify that delta U total is equal to 0 and so on, right? And then after that, right, it's then, okay, now did you do the math right to get these points, get these numbers correct or whatever, right? And that's then, that will be worth some amount of points, right? But if this is, say, a total of 6 points, probably 4 of the points would come from here, and then 2 points would come from here, right? So again, the majority of kind of what I'm looking for in this class, especially say on exams, right, is not did you add, subtract, divide, multiply, exponentiate numbers correctly, right? It's did you identify what are the relevant things that we know? Did you identify what are the relevant equations to solve for what we're trying to solve for, right? And so that's what I want us to try to make sure we have a good understanding of, a good focus on, right, as we go through the semester. So questions about this problem? All right. So we'll just talk briefly about expansion work. We'll do a lot more of this on Friday. Okay. right? And there's to basically summarize expansion work. You can look at the lecture slides to see kind of where you get this from, right? But in general, if I have some small change in volume, okay, so dV here, right, some small change in volume, right, we derive this in the lecture slides by looking at a piston here and looking at some small change in height. And the fact that small change in height corresponds to some small change in volume based off of the area in that piston, right? So if some small change in volume is times the external pressure, the minus sign here will give you some small amount of work that has been done. Okay. So dW, right, some small change in work is related with negative times the external pressure times some small change in volume. Okay. And this is true for any type of expansion, compression type work, right? So if you're talking about work that's done through expanding or compressing a gas, right, or against gases and such, right? Again, you can often think of a piston. Okay, right? Right, this expression for work, right, the change in work, right, is going to be always true. There's no assumptions, no approximations that are being made here, okay? So just keep in mind, right, that this expression, right, there's that built-in minus sign into this equation, okay? And the fact that the pressure here is the external pressure, right? The pressure that this piston is being expanded against or compressed by, okay? That external pressure, right? Not the pressure of your system, but again, the external pressure is what matters here, okay? In this expression, right? So questions about this, right? We will use this expression on Friday to derive what the work, how to calculate the work for different types of changes in state, right? For constant pressure, for reversible, isothermal, and such, okay? And we'll take this approach through a lot of things. We're going to talk about heat. We'll talk about, right, what is like dQ equals blah, 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 things like that, right? We'll talk about these small changes in heat, small changes in work, small changes in enthalpy and things like that, and get these more general expressions true for any type of process. And then we'll apply these things to specific changes in state, and they'll typically involve some type of integration and derive then equations that are relevant to certain types of changes that are being done. Okay? You will not have to rederive these equations on exams. The previous teacher of this class had students do that. I don't feel like that's as useful and valuable of a thing to do. But so you don't have to rederive these equations, but you will need to know how to use them and when to use them and so on. Right? And we'll get lots of examples and lots of practice. Okay. But here, let's try to use this equation, okay, to calculate the work done when I take 0.21 moles of a van der Waals gas. Oh crap, I didn't give you the van der Waals constant, so we'll just do this in general, okay. So I'll just work this out in general. I forgot to give you the constants here, right? nRT. So you're not given all the information to actually numerically solve for this problem, but we'll kind of do what we can with what's given. So for the sake of time, I'll just kind of go straight into working this out with you guys. Okay. So basically, so again, when I start these problems, this is, the approach I take where I write down relevant equations, relevant bits of information from the problem that are useful, right? We're told the total number of moles, we're told an initial volume, we're told a final volume, we're told the temperature, right? We're told the change is done under mechanical equilibrium, okay? We know how to get, currently this is the only equation we know for work, right? So we're going to be using this equation, right? And we know the pressure for, right, the equation of state, if you will, right, for a van der Waals gas is given by this equation here, okay? Right, and the other thing to write down is mechanical equilibrium is stating what? What does that phrase mean in terms of pressure? Right, pressure of my gas equal to that external pressure, right? So if I want to get the total amount of work done, that's going to be integrating out from some initial volume to some final volume of this change in work, which plugging in for what dW is, right? This is minus integral from initial to final of P external dV. But P external is not constant. It equals the pressure of my gas. So I'll plug in what the pressure of my gas is, right? So that work is equal to the integral of V initial, V final of nRT over V minus NB minus AN squared over V squared dV, right? Okay. And then I would do this integral, right? So work is equal to minus, right? This integral comes out to be the integral of, right, 1 over x, if you will, is ln of x. So this is n RT ln of v minus nb. Okay? And then this is going to be plus an squared over v, right? The integral of 1 over x squared is negative 1 over x. And so the negatives go away and that's plus. And then I evaluate this at my initial and my final volume, right? And so now, since I've gotten this problem to give us what B is and what A is, can't actually numerically solve the problem, right? But the final step here would be to plug in for all these different constants and things like that, and then plug in for the final volume, and then subtract off what it is when you plug in for the initial volume, right? And that would give you your total work. Okay. But the main reason why I put this problem here at the end is because it's a lead-in for what we'll do on Friday, where we'll basically be taking this type of approach, right? For given a certain type of change in state, right? Right? Some way I'm changing my system from state A to state B, some path that I undergo, right? I will find what the work that's done for that path is basically just related with the integral, right, of dW, which we, then solve for by using this relationship up here, right? So again, I kind of want to just use this as a lead into that. Is what we'll be seeing on Friday. Okay. Questions about what I did here? All right. So I believe, let me just double check. Yeah, that was kind of the last kind of question slide here. So we'll end it for today. Again, I continue to try to end a little bit early, just so people can take their time leaving, don't feel like they need to rush and congregate at the doors, right? But yeah, so anyone on Zoom has any questions, I'm happy to answer them as well as anyone here that has any questions for me. I'll stick around for a little bit. Otherwise, I'll see you on Friday. Yep.
The quiz questions that we went over Monday,
Uh-huh.
did you happen to look at the Canvas answer?
Yeah, so I updated last night. I updated the answer to the one problem that I like. What I realized I didn't do is I didn't multiply my answer by 10 to the minus 5, and so that's why I ended up with the number I did. And so yeah, I fixed that. In terms of numbers, like I saw a couple of people for question 2 or 4, I forget which one, that had like 0 as an answer. But not a lot. And so I don't know what is going on there. I tried looking on Canvas to find out about that. I've seen people uh, complain about that problem. I haven't yet found like a thing of saying, oh, it's because you're using this web browser or this OS or things like that. I have read different things about scientific notation potentially being implemented in Canvas, but then it got broken and it potentially got fixed sometime last year. I don't know. I haven't tried using that, but so you could always try entering in like 5e minus 6 or something like that to see if that works. But yeah, so I've looked into that. If you are one of the people that had your answer changed to 0 or whatever, feel free to shoot me an email and I can look at that and I can try to correct your specific
Okay,
kind of thing.
mine didn't do that, but
Oh.
when we went over it, I did, the answer that you got was the answer I got, so just,
Oh, you mean are you talking about the like collision distance or mean free path problem?
yeah.
Yeah. So I
Okay.
fixed that. But I didn't fix it until like last night.
Oh, okay, so I guess
So-
it hasn't updated then.
Yeah, yeah. I'll check to see. It should update the scores. It sometimes takes it like a little bit to update them, but hopefully it's updated them by now.
Okay.
But if you check like your quiz or something and it's still showing that it's marked wrong, please let me know, and I'll try to see like what's going on.
Okay, thank you.
All right.
Have a good day.
All right. All right. I'm going to close out Zoom here.